Stuff, and then for the hard part, I'm handing over to Maximillian. This is great. The slide doesn't say that we're all from Ruhr University Bochum, and there were two students of us involved, Robin and Fabian. Wonderful. Yes, we have the kitten stuff already introduced. So what our work is about is offline password guessing. You all are aware what offline password guessing is. This means you have some form of information, for example, a hash string or something else that you can verify your password guesses offline on your computer, which means you're not restricted to a certain number of guesses, like for online guessing that we heard two talks in advance. Wonderful. So for offline guessing, there's a large number of tools available. You're all aware of that. We heard many examples mentioned before here during the talks. Hashcatcher on the Ripper, probably among the most famous ones. And this huge number of available guessers means it can sometimes be hard to decide which one is the right one for your application. And in order to compare those guessers, I'll say something in a second on what metrics we are comparing on. We designed a framework for comparing password guessers, and we are requesting feedback if you are interested in that topic about what we are doing right, what we are doing wrong. It would be great to get more information from the audience, either now or later per email. Maximillian will tell you more precisely what information we are interested in on one of the next slides. So the basic question we are trying to answer is, well, which tool is better? Now, that is a very broad question, and it might be pretty obvious that this question is very, very ill-posed. A number of problems. I mean, what does better mean? It doesn't mean my data format is supported. Does it mean it's easier to use? Does it mean it's easier extendable? Is it running on GPUs, FPGAs, ASICs, whatever? So that question is not really helpful for what is following. Let's try another question. Which tool is faster? This is slightly more precise. Still, the question is faster on which hardware, against which hash, which training set, which testing set. Too many questions to answer. And this is all just to illustrate that we are, on the next slide, making some fundamental restrictions on what we are exactly comparing. And this is for motivating why we need to restrict quite drastically. And I want to try to motivate the restrictions that we made so that you are knowing what's going on. So if we are stepping 3 or maybe even 7 steps backwards, how does offline guessing work? We are guessing a candidate. We are verifying if it matches the hash or whatever information we have offline. And if it doesn't, then we rinse and repeat and do that as often as necessary to find a password or a string that matches the verification equation. Now, this slide also is trivial enough to earn a kitten, but the important thing, and this is why I'm showing that really simple slide here, is we are interested in the first step only. So we are abstracting away of the workload required to compute this hash function. We are working on plain text, clear text password lists. We are interested in how does the tool generate the password candidates. Is he doing that in the best possible way and order? And this still depends on enough parameters to be interesting, but this makes the question which tool is faster much more tractable than what we have seen 2 slides ago. So to motivate that further, or also to defend that against the obvious criticism, if we are restricting to the number of guesses made, we are, first of all, and that's definitely on purpose, getting rid of the actual computation of the hash. So we are not considering those optimizations. They are pretty much orthogonal to what we're doing here. There are some interesting cases in between where you cannot clearly separate the speed of computing the hash function and the guesses made. And those are corner cases like, for example, Jens Stoiber's attack on SHA-1 presented here 2012, I believe, and many similar things also that require a specific order of the input files in order to be able to optimize better Stoibus attack, Jens attack particularly required that only the second word, the first word, so the first 4 characters did not change and all the others are allowed to change. So we are not capturing that by measuring only the number of guesses made. Also, we are ignoring the speed of actually generating the guesses. We are assuming that, kind of implicitly assuming that our hashes are slow enough so that basically everybody else doesn't really matter. This is slightly exaggerating. Of course, we are still measuring how long the generating tools are running, but this is not our main concern. We are mainly concerned in the number of guesses made. Second decision that may meet objections, we are concentrating on fully automated guessing. So we are not ignoring, but we are purposefully not considering the fact that humans in the loop are definitely helping in improving the guessing performance. There are papers from this year, I forgot the conference, Usenix, I believe, that actually measured that. I mean, what everybody knew, they measured it and they showed, yes, a human can do better. However, first of all, it's really hard to measure that in an automatic framework for the obvious reasons. Also, what they really required is that you are cracking a number of passwords that are following a somehow similar structure. Only then a human can detect the structure and then adapt the rules or adapt the guessing process or whatever needs to be done. For example, if you're facing a single TrueCrypt volume, then there's not much feedback that you can use because you will never get a hit until you have a hit and then you're done anyway. So this should serve as a kind of a motivation why fully automated attacks are interesting and are worth comparing. And I hope you buy these arguments. If not, let us know after the talk. This is the kind of feedback that we are interested in. And some other design decisions that we tried to fulfill is we wanted to have a framework which is very flexible, expandable. We only wanted to, and also we did, implement a kind of a basic framework that should be, to the best of our knowledge, extendable in all directions that are sensible. And that's one point where we are requesting feedback as well. And it should, of course, be easy to use. This is claimed by probably everybody implementing a tool. And we believe that we kind of succeeded here. And as I said, now that it gets interesting, I'm handing over to Maximillian and have fun with Maximilian's rest of the presentation. Yeah, it's really cool you have 2 microphones to hand over. This is complicated.
Okay, so thank you very much, Markus. I want to explain how our framework works. And just to recap, we don't want to compare password guessing tools like John the Ripper with Hashcat. We want to compare the modes of operation. So how are those passwords generated? And the motivation for this is that password hashes getting slower over time. For example, in the current Ashley Madison leak that contains bcrypt hashes, a brute force attack is no longer feasible. So there need to be a smarter approach, and those algorithms that generate passwords based on this, we want to compare in our framework to identify which algorithm works best for what data leak. So our framework considers different inputs. We, of course, work with existing password leaks like RockU, Yahoo, and so on. However, we don't want to crack any hashes, so we work on plain text only. We have implemented a module that we also support hashed input, but we, for example, do not have a functionality out of the box to save the correct passwords. So we want to compare the guessing performance and not crack passwords. And of course, we have also a module for more complex input. This might be an ethical issue. However, current password leaks also contain sensitive information like the date of birth. And there are papers that state that this information can be quite useful to generate password candidates based on this information as well. So we support a variety of input formats, and this list is not limited, and it's flexible and can be extended easily to your input format. Of course, it also includes the popular with count format because it's very important to do this probabilistic password modeling to have the duplicates in a password leak, and we want to save storage on hard disk. Then we use this with count format. Then we have an integer stating how often this password occurs, and then the password is separated by a space, for example. Our framework, as already mentioned, was designed with ease of use and the most important fact, the automated execution. So if you develop a new password guesser or improve an existing one, then you want to run a variety of experiments to prevent this overfitting, right? That you train on a specific password leak until you improve that much that maybe for another user distribution, for another password leak, the performance decreases. And as I already mentioned, if you provide a hashed input file, then we need some sort of cracking, and this is done by a hash evaluator. We used, for this reason, John the Ripper in the community-enhanced Jumbo version because it supports, in my opinion, the biggest list of input formats, so the biggest list of hash formats, of hashed inputs, like, I don't know, bcrypt, MD5, and so on. And at the end, we get nice graphs, CSV files. They are easy to compare. We have a live and interactive visualization of the current progress, and we have static graphs that can be, for example, used in a paper. So to go into more detail, our framework consists of 3 modules, starting with the preparation, after this the execution module and the analysis module, and want to explain it in a little bit in more detail now. So the preparation module, the first one, just creates jobs based on what you try to do. So you input a training set, you input the evaluation set, you input the number of guesses required you want to test, and out of this a job object is generated. This is forwarded to the execution module. The execution module, of course, needs this training set. I just called it password leak, and a guesser. This guesser is a script. We call this guesser wrapper script, as we need to support even unknown guesses. I will explain it now in a little bit more detail. And based on whether the input is in plain text file, so 1 password per line or 1 hash per line, then we have this separation. So in the first case, it's forwarded directly to our analysis module, and in the other case, we pipe the candidates and, of course, the evaluation set to John the Ripper, and he will do the comparison or the cracking, and the results are then forwarded to our analysis module. So to start with those guesser wrapper scripts, I want to explain why they are necessary. A guesser wrapper script becomes or gets the training file and the number of guesses as input and outputs the passwords, right? So the most basic guesser wrapper script you can think of is a simple echo 1, 2, 3, 4, 5, 6. And that's it. So this wrapper script only guesses the most likely password, 1, 2, 3, 4, 5, 6, and does nothing else. However, there are password guessers like the probabilistic ones like Omen or PCFG that requires a special training phase. And for this reason, we also provide a training file. If this training file is not used, like in the case of prints, then it can be ignored. But otherwise, don't hurt me, okay? Otherwise, it will be used in this script. So an example is given here below. There is this script for Omen. We execute a training phase, as you can see here, and after this, the guesser is executed. And everything that the script does is printing out those passwords, nothing else. But using those wrapper scripts, we also support not yet developed unknown leaks as well. That is the reason why you can see it here. And next important module is this plugin engine. The plugin engine is used to provide an in-depth analysis of the generated passwords. So for example, the already mentioned partial guessing entropy from the other talk can be implemented as a plugin, for example. Then we will hear something about the Ashley Madison leak today. And for this leak, it is required to apply some capitalizations on the guessed passwords. And this can also be implemented. We already did this in a project in our framework by such a plugin. Those plugins are executed during the job, so they have access to all generated candidates, and those plugins need to be written in Python. And for example, you can also write a module to store the correct candidates, so you have a list of the correctly guessed passwords for further analysis. Then finally, to make this picture complete, there are other modules, like for example, this final processing module. This is executed after the framework has finished, and it's just to get this idea of a fully automated thing. We can get, for example, the framework to send notifications based on push or email. So you can receive, like here you can see in the screenshot, a notification, hey, your job was executed successful, or all of your jobs. So for example, for our experiments, we want to execute 400 different measurements. And then at the very end, I will receive this notification, and I don't have to care about it. I started on Friday evening, and then Monday I received this notification, and I know now I can download the results and work on them. And it can run, of course, arbitrary scripts, for example, to publish the results on a website or to back up the data. Finally, there is this visualization module that is important. First of all, we need to know what is visualized. This is an example of measurement data. So we have a log file. For this example, we executed the Prince guesser trained on RockU attacking the Gmail leak. And in this result file, we see, for example, that the Prince guesser generates duplicates, as you can see here, which of course is not desirable. And as you can see, those list is not complete, so we really want to have feedback from the community, what to implement. Of course, you can write plugins for it, but we can also support it out of the box. And there's this progress file, which is important for the graphs I will show to you. So there's the number of guesses shown, the number of found passwords, and the percentage of the complete list, how many % of the file was recovered successfully. So this way we can plot such dynamic graphs during runtime by implementing a very basic web server in Python. You can forward this via SSH, as we have heard before, and you have a convenient way to see during the runtime how far the current job queue is, what are the first results, is this promising, should I change something, and so on. And of course, there are static visualizations as well. Those are required for papers. They are automatically built. So in this graph, you can see a comparison. This is trained on RockU and executed 10 to the power of 9 guesses. And you can see that different password guesses perform quite differently, right? So PCFG perform different to Prince, and Prince is working different to Omen, for example. And this is the data we are interested in, right? We want to compare password guesses, and it's fully automated build. For your convenience, we think of the idea to build a website to have this information online, that you do not have to execute those jobs, but instead just download the results. So we think of a website to implement this and list different password leaks, also include in recent ones, and execute this on all state-of-the-art password guesses. And now we have also those guesser wrapper scripts, so you can see what is exactly executed, what are the parameters, what is the smoothing, for example, and so on.
Don't just think about it.
Do it.
Please.
Okay. We need to find someone. Okay. So the question is, how can your research benefit? As you might see in the picture, this was photographed on, I don't know, Tuesday or something. We are actively working on improving password guessers, and for that the framework is very beneficial. So you have a way to fairly compare different guessing strategies. You can automatically run a huge number of experiments, and this facilitates the development of new guessers which are unknown yet, or improves existing ones. So in the future, we want to have feedback, because developing such an application isn't an easy task. We want to have the parameters, the configuration files, word list, mangling rules, everything you use on a daily basis, and want to know more about it and think about how we can integrate this in our framework. So it would be nice to have some emails in my inbox about how you execute your guessers, with which parameters are the most successful for what, and so on. The takeaway: comparing password guessing strategies isn't easy, and we build a framework to automate this process and have a way to fairly compare them. And your help is very much appreciated. So please describe your setup, send us your parameters, your configuration files, and stuff like that. So, and if you have any questions, feel free to ask.